the Nimitz-class carriers had served as the global standard for naval power projection across the oceans for over half a century. They are designed during the Cold War to launch heavy strike fighters against the Warsaw Pact and other adversaries. Those 10 supercarriers formed the core of United States naval aviation. Yet, as naval warfare shifted in the 21st century toward large networks, automated systems, unmanned aircraft, and electronically scanned array radars, the constraints of the Nimitz class became apparent. In response, the United States Navy developed the Gerald R. Ford-class supercarrier. While the high-level forms of the two classes appear familiar, the power generation, deck layout, aircraft launch and recovery technology, and combat management systems represent a fundamental departure from the 20th century engineering on the Nimitz class. In this video, we cover 10 of the most profound upgrades on the Gerald R. Ford class from the preceding Nimitz class supercarriers. We begin with the foundational source of energy supporting all of the new technologies on the Ford class. The new Bechtel A1B nuclear reactors produce roughly 3 times the energy output of the legacy Westinghouse A4W reactors on the Nimitz class. Steam turbine propulsion remains the prime mover of the drivetrain, but the architecture based on the A1B reactors is what makes possible the massive electrical power generation. Modern naval warfare and modern naval systems are extremely power-hungry, and the Nimitz class has been operating near its upper threshold as it incorporates new technologies. The A1B reactors eliminate the ceiling. In fact, they generate more energy than the Ford class currently needs, which provides the structural headroom required to integrate future power-hungry systems, including directed energy weapons, high-power radar arrays, and more advanced computing systems, without sacrificing propulsion. Second, effective space for the flight deck was expanded by fundamentally changing the footprint of the island superstructure. Engineers reduced the island in terms of size and shifted it 43 meters aft compared to its position on the starboard of the Nimitz class. This repositioning opens up critical deck space forward of the island, creating a much larger, unobstructed area for rearming, refueling, and moving aircraft. Placing the island further back also improves the field of vision over the entire flight deck for air traffic controllers overseeing landing operations, while simultaneously reducing the mechanical turbulence generated over the deck during recovery operations. Aircraft also encounter less erratic wind and turbulence as they approach and land on the Ford class. Third, flight deck configuration was further optimized by reducing the number of main aircraft elevators from 4 to 3. Designers eliminated one aircraft elevator on the starboard side of the Ford class, which on the Nimitz class was aft of the island. On the Nimitz class, 4 total elevators sounded superior on paper, but operational experience shows that having 3 starboard elevators in addition to the 1 port elevator frequently created congestion and disrupted the movement and the arming of aircraft around the aft flight deck. Removing it opened up a vast unbroken deck area on the starboard deck edge. Aircraft can now park, maneuver, and prepare for launch along the starboard side without blocking the movement of other aircraft heading toward the catapult. Fourth, the reclaimed flight deck footprint enabled a new operational model known as the pit stop. On the Nimitz class, fueling and rearming an aircraft required multiple deck movements across separate areas, creating traffic jams and increasing taxi time for airframes. The Ford class introduces consolidated pit stops along the starboard deck edge, modeled after motor racing pit bays. An incoming fighter taxis directly into a designated pit stop, where designated deck stations provide fuel, weapons, and electrical power simultaneously. The aircraft is serviced, rearmed, and turned around at a single location before taxiing directly to a catapult, drastically cutting handling times. Fifth, let's talk about the aircraft catapult. Launching carrier aircraft on the Ford relies on entirely new technology. The electromagnetic Aircraft Launch System, or EMALS, replaces the traditional C-13 steam catapults used for decades on the Nimitz class, and previous to that on the Kitty Hawk and Forrestal classes. EMALS uses a linear induction motor that drives a launching shuttle along a track using controlled electromagnetic energy. Steam catapults deliver a volatile energy spike at the start of a launch, which causes substantial structural stress to airframes over time. EMALS provides smooth, highly tunable acceleration. This precise energy management allows operators to dial in the exact force required for a given airframe weight. As a result, the US Navy can launch heavy strike fighters fully loaded with ordnance, like the F/A-18 Super Hornet and the F-35C stealth fighter, and then instantly recalibrate to launch lightweight uncrewed aerial vehicles without damaging their more fragile airframes. EMALS is also less exposed to corrosion over time and less mechanically complex, reducing maintenance requirements compared with the steam catapults on the Nimitz class. Next, on the other end of the flight deck, arrestor wire systems that enable landing operations receive a parallel upgrade. The advanced arresting gear of the Ford replaces the heavy mechanical and hydraulic ram systems of the Nimitz class with software-controlled electric motors and rotary hydraulic absorption systems. When an incoming aircraft catches the arrestor cable, sensors calculate its weight and speed in real time, allowing the electric motors to apply dynamic, smooth resistance throughout the recovery. This precise control reduces peak mechanical stress on the landing aircraft and the wire itself. Again, like the EMALS, the advanced arresting gear accommodates a far wider range of aircraft weight than the Mach 7 hydraulic arresting gear on the Nimitz class, enabling safe recoveries of everything from heavy transport planes to lightweight unmanned combat aerial vehicles. The advanced arresting gear also eliminates the labor-intensive maintenance associated with the traditional high-pressure hydraulic arresting gear. The Ford class also has a built-in diagnostic system for the advanced arresting gear to assist with any maintenance operations. Seventh, all of these improvements, from the redesign of the flight deck to the EMALS catapult, work together to deliver a projected 33% increase in the sortie generation rate under surge conditions for the Ford class compared to the Nimitz class. The surge sortie rate refers to the maximum operational rate at which a carrier can launch and recover combat aircraft during a short window of combat. Under high-intensity combat conditions, a Nimitz-class carrier is rated to generate up to 120 surge sorties a day. The Ford class, through its streamlined flight deck, pit stop model, and rapid aircraft launches using EMALS, is built to deliver up to 160 surge sorties a day. A sortie is defined as one operational mission flown by a single aircraft from takeoff to landing. By eliminating physical bottlenecks, streamlining the movement of airframes, and using better technology, the Ford class becomes a far more efficient mobile airfield, potentially putting more weapons on targets in a given amount of time than the Nimitz class. Number 8 is reduced manpower requirement. Automation embedded throughout the ship drastically reduces the human labor required to operate it. Self-monitoring systems, diagnostic systems, simplified control for nuclear plants, and lower maintenance launch and recovery systems cut the required ship complement by roughly 700 sailors. A Nimitz-class carrier operates with around 5,200 personnel, whereas a Ford-class carrier reduces that figure to roughly 4,500 personnel. Beyond freeing up living space and improving quality of life for the crew, this reduction in personnel also yields massive financial savings in operating expenditure. Personnel costs form one of the largest expenditure categories in the Navy, and this personnel reduction saves billions of dollars over the 50-year service life of each Ford-class supercarrier. Upgrade number 9 is the introduction of advanced weapons elevators. Moving ordnance from within the ship to the flight deck to arm fighters was a historical vulnerability that received a total overhaul. On the Nimitz class, weapons elevators relied on complex steel cables and hydraulic systems to lift bombs from deep magazines up to lower deck staging areas, where sailors manually transferred ordnance across the lower deck to elevators connected to the flight deck. The Ford class introduces advanced weapons elevators that use electromagnetic linear motors to move heavy munitions directly from deep magazine spaces all the way to the flight deck in one trip. These elevators carry up to 10,900 kilograms of ordnance per trip, far exceeding legacy systems on the Nimitz that carry only 4,800 kilograms. The Ford's advanced weapons elevators are also 50% faster. All of these advantages mean less manual labor required, moving weapons faster and safer, and increasing the combat readiness of fighter aircraft. Furthermore, the advanced weapons elevators feature blast doors that seal automatically, maintaining watertight and fire-safe compartmentalization. The final major upgrade is to the radar systems that improve situational awareness and air defense capability for the entire carrier task force. The Nimitz-class carriers rely on multiple mechanically rotating radars, which presents lower refresh rates and variable radar resolution, and, generally speaking, lower resolution for the same bandwidth and wavelength than modern electronically scanned array radars. The lead ship of the Ford class, the USS Gerald R. Ford, introduced the dual band radar, while subsequent ships in the class, starting with the USS John F. Kennedy, transition to the Enterprise Air surveillance radar. Both configurations replace the rotating antennas with fixed, active, electronically scanned array radar panels built directly into the faces of the island superstructure. These phased array systems have no moving parts, reducing maintenance requirements while generating tightly focused and fast-moving, electronically steered radar beams. Because these are active, electronically scanned arrays, as opposed to passive arrays, the Ford's radars can generate multiple beams at the same time, increasing resolution even further. The result is a surveillance system capable of simultaneously tracking high-speed anti-ship cruise missiles, hostile aircraft at long ranges, and surface threats across complex environments involving substantial sea clutter. Taken together, these 10 upgrades turn the Ford-class supercarrier into the ultimate mobile airbase. Despite similar appearances, the Ford is not an incremental improvement from the Nimitz. It is substantially better in basically every way, from the efficiency of flight operations to the range of usable aircraft and to survivability. The greater energy yield of the Ford's nuclear reactors and the substantial slack capacity in available power mean that future technologies can be easily embedded, making the Ford even better in a way not possible for the Nimitz. The teething issues associated with certain systems on the USS Gerald R. Ford, like the EMALS and the advanced arresting gear, have been largely addressed, which will shorten the workup period for subsequent ships of the Ford class.